Global PageRank ranks the whole graph, but recommendations often start from one node. Personalized PageRank turns that seed into a local ranking. You'll learn the shape of a workflow that scores nodes from a seed and highlights the most relevant neighbors. I'm Professor Pi, teaching AI foundations with simple Python. Personalized PageRank is the go-to when one user or one product should drive recommendations. You want neighbors that are locally relevant to a seed, not a global authority score. That matters when you recommend content, friends, or similar products from interaction graphs, where topology and directionality carry meaning. Think of it like this. A random surfer who keeps restarting at one user will naturally spend more time near items that connect tightly to that user. Those high-probability nodes are the things you show. The method uses graph structure well and personalizes cleanly. The trade-offs are sensitivity to edge weights and to how far the walk is allowed to roam. We'll build a tiny example and tighten it up step by step. First, seed a minimal interaction graph and run a seed-biased PageRank. Next, tag items so we only return recommendable nodes. Then, add edge weights. After that, shorten the random walk so it stays closer to the seed. Finally, filter out seen items and normalize scores into a neat recommendation list. Quick note, this code is designed to teach the core idea clearly. Library versions and local setups can vary, so check the official docs if your setup behaves differently. Let's start by seeding a tiny interaction graph and running personalized PageRank from a single user node. This snippet seeds a tiny interaction graph and runs NetworkX personalized PageRank from a single user node. Global PageRank would blur the user's taste across the whole graph, so we bias the teleport vector through seed bias. G pulls 4 quick edges into a digraph so we can model directional preference flow between user and items. NX PageRank with personalization equals seed bias keeps the walk restarting at our user, even when the random surfer hits the dangling item 3. We then sort ranks to show the highest probability nodes that stay close to the seed without yet filtering types. The printed seed top 3 list confirms which nodes surface first for that user-focused walk and why they anchor the later steps. The initial run mixes user and item scores, so the user still shows up among the top hits. That's not useful for recommendations, which is why we add role tags next. This example tags item nodes inside NetworkX so we can filter personalized PageRank toward recommendable content. Without metadata, the highest PageRank scores would still include the user, which is useless for the suggestion list. Items builds the candidate set from current nodes, while tags pushes role labels back into G for reuse later. The comprehension reuses regs, so we skip another solver run, yet still return rounded tuples interviewers can read quickly. The printed item top 2 pair spotlights the leading items only, proving the role filter kept the recommendations focused. Raw click counts, or play durations, often tell a different story than binary edges, so we fold interaction strength into the graph. This code injects edge weights in NetworkX before rerunning personalized PageRank to reflect interaction strength shifts. Treating every click the same would keep item 1 and item 2 tied, even when one is clearly more popular. G.add weighted edges from updates the existing edges, so the walk spends 3 times longer on the item 1 branch than on item 2. NX.PageRank with weight equals weight respects those counts, and weighted shift compares the new solution with the original ranks without another manual diff. The printed weighted shift tuple shows item 1 gaining 0.08, while item 2 drops by the same amount, confirming the weighting moved probability mass instead of inventing it. Even with weights, long random walks dilute the seed's local signal, so we make the walk restart sooner. This snippet lowers the NetworkX damping factor, so personalized PageRank stays closer to the seed neighborhood. Long random walks would otherwise keep feeding item 3, muting the fresh evidence on item 1. The multi-line nx.PageRank call keeps the wait signal while dialing alpha down to 0.6, so restarts happen sooner. Localized top 2 then reorders candidates based on the tighter walk distribution we just computed. The printed localized top 2 values capture item 1 edging ahead of item 3, showing how the lower alpha tightens ranking focus. We're almost ready to serve recommendations, but we must exclude content the user already consumed and normalize the remaining scores. This example converts NetworkX personalized PageRank scores into a normalized recommendation list after excluding seen items. Handing a teammate raw scores without removing watched content would cause embarrassing repeats. Seen items guards against that by filtering candidates from localized ranks before we ever sum probabilities. Total normalizes the surviving nodes, and final recs formats the probabilities so they visibly add up to 1. The printed final rec sequence delivers ready-to-serve item ratios, making the walkthrough feel like a usable baseline. In a production pipeline, the same pattern maps directly. Your interaction logs provide weighted edges. Your user ID is the seed bias vector. The normalized final recs become the input to a re-ranker or a UI layer that applies filters and business rules. Here's the takeaway. Bias the random walk to the seed and you get local relevance instead of global authority. Use this when graph links and direct interactions matter, and you need per user or per item focus. And remember, the ordering depends a lot on edge weighting and the damping factor, so those knobs can change what rises to the top. A useful next step is to tune the damping factor and the edge weight scaling on your interaction logs, comparing recommendation list on a holdout set before deploying. That single change often produces the largest practical improvement for this exact toy pipeline. If AI Foundations in Python help, subscribe and watch the AI Foundations videos.